Today I'm really excited because we get to talk about energy, and there's two different types of energy that we focus on in the sciences, kinetic and potential. And as chemists, we're really interested in both of these things, and we'll kind of talk about why throughout the course of this little video here. Now, energy, from a scientific standpoint, everyone kind of knows what energy is, right? You kind of have energy to do things, right? If we think about it in kind of a colloquial way. But in energy, for a scientific definition, is the capacity to move matter or to overcome some sort of resistance or to do some kind of work. And overcoming resistance sounds a little bit, hyperbolic a little bit, like I'm pushing against some sort of great tsunami or something like that. But overcoming resistance just means that I'm going against the natural tendency of something, right? The pen here is at rest. When I lift it up here, I'm overcoming gravity's pull on it. So I'm applying some sort of work to it, which means that I am putting in energy. It's not going to do this spontaneously. I had to put in energy in order to cause it to do that. So that's the capacity to move matter. That's really how chemists think about this, is in terms of materials and matter, because that's what chemistry is all about, is the study of the structure and behavior of materials and material things. And so some of that is kind of how we move things around and how we exchange this energy and what we can do with this energy when we get it out of chemical processes, that kind of thing. So there's two types, and I know this is going to be a review because you've seen energy in all sorts of physical science classes throughout the course of your education, but there are kinetic and potential energies. And kinetic is the energy of motion or movement. That's right there in the term, right? Kinetic means moving around. And if I'm going to talk about this mathematically, then kinetic energy, or Ke, is usually the way that I will talk about it, as Ke, or you'll sometimes see it in textbooks or on websites as E sub K, is equal to 1/2 mv squared, where m is your mass, v is your velocity, that's the movement part. So the speed at which you're moving, you square that, you multiply it by the mass, because of course the mass is important, because how much stuff you're made up of, how much matter you're made up of, is going to impact how much you're moving. And then potential energy, I like to think of as the energy of position. So I kind of like the parallel nature of calling kinetic energy the energy of motion and potential energy the energy of position, because that depends on where you're located in the universe. So you'll sometimes see E sub P for potential energy. I prefer PE, and you'll see that in most of my videos. I try to use them interchangeably because you'll see both. That's going to be equal to, again, the mass, because we're talking about matter, times G, which is gravity. So the gravitational pull on that matter, which mass and gravity together kind of give you your weight. It's a force. If we're thinking about it in terms of units that we use here in the US, then that would be what you'd see on a scale when you're measuring weight, as opposed to mass, which is just measuring how much stuff you're made up of. And then here's the position part. This is the height. So the units for this then are joules. That's our SI unit for this, the standard, international standard unit that we use as scientists. We'll use kilojoules sometimes, but joule is the standard unit. So sometimes we'll see things specifically in kilojoules, and we'll talk about that with the different thermodynamic quantities later on. So thermodynamics is the study of the change in energy of a system, and so that's kind of what we're introducing here with this idea of energy. So a joule then is what we use as chemists and as scientists in general. This is equivalent to a kilogram meter squared per second squared, which looks kind of wacky, but we're relating all of our different SI units together. And if we look at this unit, then this comes, you can see, from the equation for kinetic energy. If we take 1/2 our m, our mass, that's going to be the kilogram part of this, and then v squared, velocity is in meters per second in our standard units. So if we have meters per second squared, that gives us the meter squared per second squared part of our joule. So sometimes you will see joules as kilogram meter squared per second squared. That's going to be an important relationship when we're solving problems dealing with joules and with energy in general. Now, we in the US customary system, we use calories. So calories are kind of what we see in terms of our food packaging. That's the way that we measure energy in general. So calories, by definition, are the amount of energy that it takes to raise the temperature of 1 gram of water by 1 degree Celsius. So if I wanted to get the water to go from 20 degrees Celsius to 21 degrees Celsius, and I have 1 gram of it, so that would be, 1 cubic centimeter. So if we're picturing kind of length times width times height of a little centimeter there, that much amount of water, the amount of energy it takes to go from 20 to 21 degrees Celsius is 1 calorie. And this is called the specific heat capacity of water. And heat capacity and specific heat capacity are going to be important concepts that we'll see in some future videos. But we use the specific heat capacity of water as a defining characteristic for our unit of energy here in the US, the calorie. Now, this is not to be confused with food packaging calories, which are kilocalories. So if you see something has 5 calories in it, then it's actually 5,000 calories. 5,000 calories by this definition. So that is an important thing to keep in mind as well. Now, this is not to be confused with power. We think about power oftentimes when we're thinking about, powering our home and what do we use energy for. We think about energy in terms of the way that we light light bulbs and allow our computers to be on and our dock cams and all those kinds of things. So power is actually a slightly different thing. It's measured in watts. Think like the wattage in your light bulb. So power is actually a rate of energy transfer. So a watt is actually a joule per second. So that's a rate. How much power, how much energy you're using per second is the wattage. And so if you have a 100-watt bulb or a 60-watt bulb, then that 60-watt bulb is going to have 60 joules of energy used per second. So that's the power that it can put out, how much it's transferring that energy to light energy, for example, if we're talking light bulbs. So these guys are kind of often confused because we think about power and we think about energy as sort of the same thing, but they're related, of course. So the joules are right in there, but it's a rate, so per time. Now, in terms of calories to joules, just in thinking about our units, 1 joule or 1 calorie is equal to 4.184 joules. And that's kind of one of those relationships that's going to be important. It'll probably be given to you if you have a kind professor on problems like this, because we're going between the US system and our SI unit system. So 4.184 is kind of a magic number for a lot of this. And again, it's all built around water, and we'll get into that in later videos. So let's do a couple problems to play around with this idea of energy. So if I have a ball that has a mass of 5.51 kilograms, so we're talking about something that's just kind of a couple pounds-ish, just a little bit over a couple pounds, rolls at a speed of 15 meters per second, so it's kind of cooking along there. What is its kinetic energy? So our KE is equal to 1/2 mv squared, so this would be 1/2 our mass, and it's already in kilograms, so that's good, and then our V here is already in meters per second squared, and so our kinetic energy for this is going to be 6.20 times 10 to the second joules. And again, this is kind of why it's important to understand the relationship between kilograms and our meters squared per second squared. So a kilogram meter squared per second squared is a joule, so that when you look at all that combination of units, you're like, what the heck? I thought I was supposed to have an answer in joules. Well, you do. They're the same thing. Okay, so 620 joules for that particular ball in motion. Now let's think about this ball kind of in terms of a position. So if we huck that ball up to the top of a tree, so now it's at the top of a 10-meter tree, then our potential energy is equal to our mass times gravity times the height. So the mass of the ball is the same, 5.51 kilograms. Gravity is kind of, depending on how you're given it, is going to be a constant. So your gravity here is going to be let's use 9.807. It's often given as 9.81, and this would be meters per second squared because it's an acceleration. And then your height, which is 10 meters, And when we multiply all those together and we're taking sig figs into account, then looks like we have 5.40 times 10 to the second joules. And again, joules coming from kilogram meter squared per second squared. If we analyze our units here and look at this setup, you're going to have kilogram times meter because of the height times the acceleration from our gravity per second squared. So kilogram meter squared per second squared, which gives you a joule. All right, now from a chemist's standpoint, we think about both kind of the macro level of things as well as the particle level. And really as chemists, we focus more on this particle level kind of size. So internally at that particle level, we have both kinetic and potential energy. So the kinetic energy comes from the moving particles, and all particles are in motion all of the time. You probably have heard, if you know that the concept of absolute zero, that absolute zero is the temperature at which all motion ceases, because everything is always moving around. So even if my pen here is at rest, the particles within my pen are still moving around at a particle, atomic, molecular kind of level. So that's kinetic energy. And then potential energy comes from when we're thinking about chemical bonds. There's stored energy, which is another way that people talk about potential energy, is stored energy. I still like to think about it as position, because in a chemical bond we're talking about this kind of stored energy between two atoms. And so this energy within chemical bonds can be used to do chemistry. It can be used to do interesting and useful work. And so we have some stored energy, we have some energy in motion, and together, taken together, these are our internal energy, which for reasons that I don't understand is usually symbolized by a capital U for internal energy. I feel like U is kind of the variable that they use when they have run out of other variables. So internal energy is U, and we have both kinetic and potential energy within an object because of the chemical makeup of it. Now, if we're thinking about the total energy of a system then, so the total amount of, if we're thinking about any sort of chemical process, then the total amount of energy is going to be equal to the energy that is due to it moving around, the kinetic energy, plus the potential energy. And again, you'll notice that I'm kind of switching back and forth between my symbols so that you get used to seeing both. And then also the internal energy of the system. So this is if the object or the stuff is in motion. This is based on the position of it. So if I'm doing my experiment at the top of a tree, right, then I have a greater potential energy. And then this is the internal energy of the system. Now in a lab setting, most of the time you're not running with your beaker or at the top of a tree in a lab. So in a lab, these are constant. We'll call that constant-ish, right? So under kind of standard conditions, we're not moving around too much, or relatively speaking, we're not moving around. Even if we're stirring something up, we're not moving it around to such a great extent that it's going to have a lot of kinetic energy where it's really moving around. Potential energy, you're always doing things at the same height and hopefully on Earth, or even if you aren't, you're doing it under consistent gravity kind of conditions. So these are constant-ish. So that means that the total energy in a lab setting is usually just kind of, we can consider that the internal energy plus some sort of constant. Now this gets us to an important scientific law, which is the law of conservation of energy. We've talked in prior videos about the law of conservation of mass. They are related to each other. The law of conservation of energy says that energy can be converted from one form to another. So I can go from kinetic energy to potential, or I can go from potential energy to kinetic. And that's allowed, right? I can convert form from one to another. I can also transfer energy from one thing to another. So I can transfer energy from one substance to another. I can transfer energy by taking my pen and throwing it right across my desk here. So the energy from my moving fingers then was converted to my pen, which was then under my laptop. But now I have this pen and it is it's got the kinetic energy from my hand. But the take-home message from all of this is that the total energy remains constant.